convenient. If you have a state of stress in which sigma 1 is a given value, sigma 2 is equal to sigma 3, as it happens in many laboratory tests, you're going to find out that Q is going to be equal to square root of 3 times 1/6 of, there is one of the terms there which is going to cancel out because there is no difference, right? And this is going to be sigma 1 minus sigma 3 squared, and we know that sigma 2 is the same as sigma 3, so there is just going to be another sigma 1 minus sigma 3 squared, and that's going to be 2 times that, and 2 times that is going to be 6 divided by 6, 1, and square root of this guy is just going to be sigma 1 minus sigma 3. So much easier to understand. And P is just going to be that. It's the minimum principles, the average of the. So let's write it too. P is going to be sigma 1 plus 2 sigma 3 divided by 3, assuming that sigma 2 is the same as sigma 3. So let's apply these definitions to a thought experiment, okay? Let's say that you're working for Statoil. I know they are hiring guys, so if you are interested, and they send you to the North Sea to work on an offshore field, to one of those fields with diatomites I showed you before. So you drill a wellbore, and you get to this formation. There is a cap rock over here. And because you're producing from this formation, you're going to start lowering the pore pressure. So if I were to plot as a function of time the pore pressure, let's say the pore pressure will decrease linearly. Okay? And also, you know that here there is the weight of the water, right? And the fish and all the sediments on top. That weight, it's transferred into stress and into SV. What do you think is going to be the variation of SV with time? Is SV, the overburden, going to vary with time? No, right? But there are some assumptions in doing that. We're going to say that it is more or less constant, okay? I'm going to agree with you. I'm going to plot that SV is going to be constant. And in order to assume that, of course, you know, this overburden is always going to be there. Just by lowering the pore pressure here, I'm not going to change the overburden. And also I'm going to assume that this cap rock is not holding stress. So it's a compliant cap rock. It deforms as this reservoir deforms, the cap rock also deforms, and it pushes all the time with the same weight. If you had a very stiff cap rock, then some of the load will be taken by the cap rock. But I'm assuming this is a soft cap rock, so it pushes all the time down with the same overburden. So that SV is constant.
And is there some work on like the effect of tidal height, you know, SV?
Yeah, the tidal changes, they will also change, make SV change. depending on the depth, that will be important or not. For example, for some sediments, shallow sediments that have methane hydrates, those tidal changes are very, very important because they can make fractures go at some times of the month and not at some other times. But let's assume this is very deep, okay? So those are minor changes. What do you see here? What is going on? The effective stress is increasing with time, right? And if effective stress is increasing with time, what is going to happen to the rock? Stronger? But you're right on some sense, but I'm looking for another. You're going to compress, right? We're going to see later on, and we're going to prove this with pore elasticity, that effective stress, as we know, is going to increase. That's obvious. But also, the lateral effective stress are going to increase too. And if we had, now in this QP diagram, which is very similar to this J2I1, if we have a shear failure line here, and we had something that we're going to see later on when we look in critical state soil mechanics, we have a yield cap, and let's say that we were originally somewhere over here. As you deplete, the stress path of this element is going to go into that direction with time. This is going to be the stress path for depletion. If before you do depletion, for example, you were to do hydraulic fracturing, probably at the tip of the fracture, your stress path goes into that direction. You have less effective stress. So it is going to depend on what action you apply, what is the effective stress path. It might go this way. Sometimes, depending on rock properties, it can also go that way and hit the shear line. Or if you are injecting, for example, here because you want to store CO2, as actually the Norwegians are doing, this stress path. Let me lower this hydraulic fracture tag. This stress path is going to go like that. So depending on the actions, it's going to be very useful to us to plot what is the stress with these invariants. I have one more thing to say. I'm 2 minutes over. I'm sorry about that, guys. I wanted to introduce you to Jeffrey. Jeffrey's there in the back. He's going to be the TA for this class. He already took the class last year and know how to solve the homework. So if you need help, please talk to Jeffrey. Okay? All right. So now you have everything you need to solve the homework. And if you have any questions, just let me know. Send me an email or send Jeffrey an email.